Welcome to the fourth tutorial of ITA workshop. It is my great honor and pleasure to introduce Professor Andrew Barron at Yale University. There are many researchers in information theory and statistics, but I believe Andrew is one of the best researchers representing both information theory and statistics. For example, he received his PhD in electrical engineering at Stanford, and now he's a professor of statistics at Yale University. Another example is he received IEEE Browder J. Thompson Prize Award in '92 for the best paper written in all IEEE journals written by any researcher of age under 30. And at the same time, in 2005, Andrew received IMS Medallion Award in long list of other awards he received, which represents his fundamental contributions in statistics. Andrew has very broad area of interest, ranging from statistics such as Bayes method or statistical risk analysis, neural networks, density estimation, minimum description length principle, and universal compression, or more bread-and-butter topics for information theories like entropy power inequality and Shannon-Macmillan-Bryman theorem. And more recently, he's been contributing in more applied, or in a sense, more channel coding oriented part, like capacity option code for Gaussian channels. And finally, his another passion includes model airplane building, for which he won 4 national championships. So without further ado, here is Andrew.
Thank you very much. Okay, it's a pleasure to be here and a pleasure to talk about ideas that we enjoy. And I know it's been a long day, and we've all made a great effort as listeners and as preparers. My intention is to give a sense of the sweep without necessarily talking about everything fully. So I definitely want to get to the third topic, that's the newest stuff, but it's fun to put it in the context of information and statistics broadly. And there's topics within information and probability, within information and statistics, and then the recent results on Shannon capacity. Now, is the volume okay here? Yeah, okay. So I'll go over these, in advance, and I'll review each, and we'll get into details of what we choose to. But I want to set up some of the information theory and probability core that is dear to me and to a number of you, where we want to talk about to what extent do quantities of information, by their natural monotone approach to the proper limits, give the best understanding of various phenomena, from the central limit theorem to error probabilities and hypothesis tests, to large deviation exponents, to Markov chains, to Martingales, and so on. Is information theory the right way of looking at these types of probability limit phenomena? And within that, in a couple of minutes, I'll ask for a topic or two you definitely want me to cover within that, and then we could probably skip some, okay? Just doing it on an overview basis. Now, in information and statistics, there are 2 main things I want to discuss. One is to what extent are the fundamental limits of statistics determined by information quantities, just as they are determined, in communications. The data compression limits and the channel coding limits are determined by information quantities. Is there a similar phenomena when it comes to asymptotics of statistical risk? That deals with some Minimax rate kind of flavor. But the other main thing is, when you're trying to do practical statistical fitting, you don't want to lock in some sort of function class. You want to have an adaptive procedure that can work well for many different situations. And that usually involves some form of penalized likelihood or penalized squared error. What are the penalties that are acceptable? And does information theory help resolve what are the right type of penalties for statistical purposes, as well as compression purposes? Those are the 2 main things we want to cover there. And then, and that's work with a number of former students. And then with current student, Anthony Joseph, we're working on achieving Shannon capacity for the Gaussian noise channel with power constraint. And basically, a way of thinking about it is, whereas these other problems in probability and statistics, the theme is, how does information theory inform probability and statistics? How does information theory solve statistical problems? This one is in reverse. We're going to use some statistical ideas to solve the information theory problem of making communication practical in the presence of Gaussian noise. So briefly, I guess I pointed it out already, but the two main things we want to get to in information statistics are information theoretic determination of minimax rates asymptotically, and then non-asymptotic inequalities that work for any sample size and tell us what types of penalties will give us good risk bounds that adapt to different regularities that the target function might have. And as I was just saying, for the Gaussian channel problem, we want to put it in context to talk about how a regression setup permits solution to the Gaussian communication problem, how it uses ideas that have precursors developed by some people in this room, including superposition coding and successive decoding, but how we need to deal with variants on those themes, sparse superposition coding and adaptive successive decoding to make it work rapidly. And we'll deal with rate, reliability, and computational complexity. So those are kind of acts 2 and 3 of the talk. Act 1 concerns the overlap of information theory with probability. So the theme here is looking for a monotonic approach. As you get larger sample sizes, or further down through a stochastic process, are you closer to the appropriate limits, and what are those limits? So there's issues of Markov chains, Martingale, central limit theorem, the AEP, and the exponents that go with the law of large numbers. So can I have someone suggest a topic or two from here that you definitely want me to cover? If there are none, we might skip. But yeah? Achieving capacity. So you don't want me to dwell too long on probability. Any votes for anything within probability? The information stability. So you want to get that. And one other? What? Monotonicity. That's kind of thematic for the whole thing. So if I'm not careful, I'll start saying everything. But I will at least try to point out that things we use all the time in Shannon information theory, the chain rule and the data processing inequality, are the core things. So why don't we start with that, and I can point to its use. So the information inequality says, if I have a pair of random variables, x and x prime, typically we're thinking about you first have x and then it goes through some channel or some transition probability and you get to x prime. But you might have two different distributions for x, p and p star. And those will induce two different distributions when you apply the transition, px prime and px prime star. Right? The data processing inequality, or well, I'll just call it the information inequality of information theory, says that you're closer to each other after you form a transition. Right? So it says that the relative entropy between p and p star after a transition is smaller than it was before. And we use that a lot. Now, of course, there's one core identity that drives so much of information theory and even proves this. It's the chain rule, right? And the general chain rule says that if I'm looking at the relative entropy that two different distributions would give to a pair of random variables, then I can look at it first in terms of the relative entropy on the first variable plus conditional relative entropies of the second variable given the first. If I have a pair of variables, I can expand that in either of two ways. But in my story here, we're saying that the transition rule from x to x prime is one distribution, the same either way. So one of these four terms in the two expansions is 0, right? So if you're, This is a mental exercise that I think 85% of you or more will get. Identify which of those 4 is 0. So we're focusing on that pair of distances, and the one in green is the one that's 0, right? Because the transition rule is the same from x to x prime. So that tells you that the divergence after transformation, after the stochastic step, is smaller than it was before, and it quantifies how much it's smaller by, right? It's the relative entropy between the reverse conditional distributions. And this, to illustrate its use, consider Markov chains in which P star is an invariant distribution. So a transition rule doesn't change it. So then any number of steps brings you closer than to P star than you were before. And so, of course, that means those real numbers, those dn's, form a Cauchy sequence and are hence convergent. But the Cauchy sequence property is deeper in that when you look at the difference between them, okay, it's going to be an expected ratio of the 4 probability mass functions that are involved. But that is equal itself to a relative entropy, the reverse conditional relative entropy. And Pensker had a very important inequality that says that if d is small, then the expected absolute log ratio is small. That means when a d here from the difference of these is small, you have a Cauchy sequence in L1 and hence a limit. And this phenomenon occurs in studying many of these things. It doesn't tend to be in our texts of information theory, but I would encourage us to think of that as a basic tool. I mean, what does it mean for a real numbers sequence to have a limit? It's the Cauchy sequence property, and guess what? Our basic chain rule establishes that for information quantities. So you can get results about Markov chain convergence. An early example of work in that direction was by Fritz in '72, former student of Emery Chisar's. And I alluded to this inequality. So A, if I have D is dpq, then A would be the expected expected absolute value of the log ratio. And has a positive part and a negative part. And using the Pensker-Kullback-Chisar inequality relating total variation and D, it gets used to upper bound A, and in that way establish from a chain rule that you have a Cauchy sequence property. You can do the same thing with Martingale so that we get on to our priority in other topics. Let me just say it's the same. Okay? So Martingale convergence for L log L bounded random variables is the same, and it is really the same as for L2 random variables. And there's the same type of decompositions that you would have for L2 random variables. And also, this is intimately connected with our foundations as to what relative entropy is when you get past the discrete case in the first place, right? Kolmogorov and his group in the mid-50s said you take a supremum over increasing sequence of sigma fields, so the relative entropies you would have had on each, and knowing that there is such a limit is a consequence of the Cauchy sequence property from the chain rule alone. In other words, you don't have to quote a Martingale convergence theorem. The chain rule gives you the Martingale convergence. Central limit theorem, I think most in the audience have seen some of this, and it doesn't use yet the chain rule quite as much. So I think it ought to, and it's fun in a setting to try to encourage smart people from the audience to take things further. Okay? So wouldn't it be great if we could prove the central limit theorem and its monotonicity of approach just from the chain rule? So let's give it a try, at least for a page. So it is true that you have a monotonicity of approach. So here, Pn is the distribution of Yn, the standardized sum of n IID random variables of mean 0 and some variance. And P star is the corresponding normal. And you get closer with each step. We'll quote some things on that if we want to in a minute. But let's just see what the chain rule gives. So again, you can expand both ways. And there is a Markov chain-like property happening, right? If I'm going from m to n, then I have to add n minus m more random variables that are independent of the m that I already had. So that's a kind of Markov chain. It's not a time homogeneous transition rule because you divide by the square root of n. Nevertheless, it is fun. We don't have any one of these four being 0, but this one simplifies because when you condition on ym, you just have the n minus m remaining variables. So there is a decomposition, and since we do know by other more complicated means that the relative entropy distance from the Gaussian is going down, it must mean that this distance is less than that one. So challenge, find a more direct information theory proof. And then double challenge, use that in a more direct proof of the central limit theorem. Our current way of understanding it uses another important inequality that Kim mentioned, the entropy power inequality. And in my student days at Stanford, Tom said, well, this implies monotonicity of approach on the powers of two subsequents. Can we prove a central limit theorem from it? And using some properties of the derivative of entropy, that Fisher information or a minimum mean squared error, properties that Larry Brown had elucidated, I was able to integrate that up and get the zero limit. And in later work with Oliver Johnson, could get bounds on the rate of convergence. I won't go into the specifics about the Poincare constant R. But to mention the status of getting monotonicity, you can fancify the entropy power inequality in a way that Mokshe Madiman and I were able to do, and give a simple proof of it. Artstein, Ball, Barth, and Nauer did it this way also, but we gave a simpler information theory proof. Well, it's projection properties or chain rule properties, but of the entropy derivative rather than the entropy itself. And it gives the monotonicity on the whole sequence. And useful perspectives on it are also in the work by Tolino and Verdu. So there was a suggestion of hearing about the AEP, if I remember correctly, was one of the topics. And as Tom mentioned yesterday, there's a fun proof of the AEP by a sandwich argument, right? So suppose I have stationary ergodic y1, y2, ... and let Q be just counting measure or Lebesgue measure so that it's not in the way yet. All right? Then we could just take the log of the joint density and write that as the sum of the logs of the conditional densities given the past and sandwich that between the k past and the infinite past. And that was Tom's slick proof. In the year before that, I was able to take a step beyond the original Shannon-McMillan-Bryman theorem, which was for discrete random variables, where you have the advantage that all those conditional probabilities are bounded by 1. But I had followed the kind of the protocol of Bryman, who used domination of Martingales and found a suitable domination property of the log conditional densities, even if they are bigger than 1. So by either means, we know that there is an entropy rate and that the sample version converges to it. Now, the status with regards to Q is intriguing. Certainly, it covers the case of counting measure or Lebesgue measure. Certainly also any IID measure for Q or any Markov measure are all covered by either of those arguments, either the Kovar-Alguet argument or the one that I gave, or earlier proofs that John Kiefer gave for L1 convergence, and so on. It remains open, the general properties of convergence if Q is not Markov. The problem is that when you do this decomposition, think of it in terms of the sandwich argument. You're trying to study the properties from the perspective of P. And what does the P measure have to say about the limiting properties of the Q conditionals? And it's not at all clear. But I do want to point out that there is room to say some things for arbitrary processes that don't rely on Markovity of Q. I'll say that in a moment. But first, this fits the way I teach. I introduced the information theory course to Yale, and I teach it in a way that is holistic with regards to statistics and electrical engineering. So when I come to Chapter 3 in Cover's book on the AEP, I'm covering the Chernow-Stein lemma about the best exponents of hypothesis testing at the same time and with the same proof, because it's one and the same. It's just a matter of what is the meaning of the measure Q. So you're finding for a given power, hopefully large, for the probability of A, what is the how small is the measure of the set that has most of the probability, and one can make that measure as you please. In hypothesis testing, you're interested in the alternative probability that Q would give, and it has an exponent that's determined by this rate, and fine. So I commented that this would work for any pair of processes in part. And so regarding the optimality of the relative entropy exponent, what would be a non-asymptotic version that could be useful for any pair of joint distributions for y1 through yn that Q would give and that P would give? Well, the information inequality, the theme of this part of this act of the lecture. And the information inequality that you would get by considering the Bernoulli random variable associated with the indicator of the set AN, your typical set or your testing set. If you take the P log P plus P complement log P complement and recognize that as minus a binary entropy, take one of the Q terms, the QA complement part, and say, oh, log 1 over QA complement, that's bigger than 0. Then you're left with this inequality that when you invert it, says that the Q probability of any set A is bigger than e to the minus d. And how is that d modified? And that d is the total divergence, and it's modified by division by the probability of A. So if A is likely, that doesn't, that's near 1. That doesn't change the exponent much. And H2, of course, is bounded by 1. Also, if P of A goes to 1, it goes to 0. So you can't have an asymptotically smaller or better exponent, I should say, asymptotically smaller probability than reflected by the exponent given by the kind of, instead of non-asymptotic, the literal joint entropy, joint relative entropy between P and Q on a sample of size n. So you can't do better than that exponent. And that gives for free, actually, one side of the limit statement that you would want, at least in probability, regarding the AEP, just from that information inequality. In my pecking order of important connections between probability and information theory, the work of Emery Chisar on information projection, characterization of the large deviation exponents, conditional limit theorems is high. But I think I'm going to skip it, okay? It's real fun stuff. His paper from in the mid-'80s in the Annals of Probability gives really cleanly, for instance, what we also know as the Chernow bounds given in terms of an information characterization. And I will at least point out that in all of these types of results, though in discrete situations, playing with the method of types is fun, the method of types has nothing to do with these results, and indeed could get in the way. There's no polynomial factor out in front. It's 1, okay? Whereas the method of types will give you something where you start worrying about the size of your alphabet, And that's a red herring. It's not part of the real bound. And Chizar's paper makes that clear. And this is fun for later because I use it in connection with the channel coding. When you specialize the story, so we'll end, this will be our last thing on information and probability, is a simple specialization. So suppose y1 through yn are IID coin flips, but with a bias coin p, and you take some p star bigger than p, and so you're looking out at a right tail, and you say, what's the chance that my relative frequency is bigger than that? So you're looking at a binomial tail. So it says that the binomial tail is upper bounded by e to the minus n d p star p. And other lower bounds that you may have seen in other contexts and have their own histories are consequences, like Hoeffding's inequality for sums of bounded independent random variables is a consequence because the Bernoullis form the extremal case. And you can also handle here not identically distributed. The role of P would be played by the averages of the PIs across the different random variables. But that Hoeffding inequality that gives the square between P star and P, that's the right quadratic behavior that the relative entropy has when you're away from the edges in the plot of dpp star, right? But if you're near the edges, the behavior is different and is governed by the Poisson exponent. And it's clean. The Bernoulli exponent is bigger than the Poisson exponent. And so, at least with regards to large deviation probability bounds, the binomial tail is upper bounded by the Poisson tail. So it's not just a kind of central distributional property, it's also a tail property, the relationship between the binomial and Poisson. Okay, so this forms the end of Act 1, where we've seen that the information inequality and the chain rule provide monotonicity of information useful in a number of what I think are important settings. Information stability is closely connected to the information inequality because when chain rules the sample relative entropy and because the information inequality gives half the answer. And also that gives the best exponents of statistical tests. And the information projection geometry of Chizar and Topso identifies the large deviation exponents that tells us kind of the right way of thinking about the law of large numbers or other probabilities of constant departure from the sample mean, or in general from an empirical distribution not being in being away from some set C. Okay, so those are all results that are connected to our basic inequalities we use as bread and butter in information theory. Any questions about information and probability? Yes?
So you derive many interesting properties from data processing essentially for the relative entropy. But there are many more other information measures that satisfy data processing, like any F divergence.
That's true, and that's a very good point. And they're all, there's some interconnections, like the Hellinger, squared Hellinger is a very important one because it's the one that's a square of a metric. And as long as you're talking about F divergences where F is smooth at 1, they're all locally the same to within constant factors if you're talking about densities that are bounded ratios. And so the local properties of Kullback-Leibler are in part understood through local properties of Hellinger, for instance. We'll come back to that when we need a metric. If we have to have a triangle inequality, use it with Hellinger. But fortunately, the relative entropy is appropriately asymmetric and appropriately doesn't satisfy triangle because that's important to data compression properties and it does have the right information Pythagorean identities as Chizar and Topso have identified. So I think it's actually the large deviation problem that shows most stringently the importance of using relative entropy. I think for the others, you could argue, couldn't we get similar things with other Fs and F divergence? And I would agree. We end up with a favorite, don't we? It might be deeper than that, though, because in the case of the central limit theorem, the Gaussian is maximizing the entropy subject to a variance constraint. And if you go to other F divergences or Régnier entropies, of the different F, those might be more suitable for certain stable laws, as some recent work of Mokshe and others are investigating. So, depending upon the limit theorem you're heading towards, different quantities may be relevant. If you're heading towards what is the set that contains most of the probability, you need the typical set defined through relative entropy. If you want what's the error exponent to the best hypothesis test, you need relative entropy. Okay, good. Any other questions on information and probability? All right, so we take a deep breath and move to Act 2. And I'm rooting for all of us to, this is a long day of some nice long tutorials, but it's going to take some energy on all our parts. So Act 2, we want to get into fundamentals of statistical estimation, both in identifying minimax rates and what role does Shannon theory have to do with that, and then the formulation of adaptive statistical procedures through asking what are the right types of penalties to put on likelihoods. And the MDL criterion is kind of the prototypical example of that, but what other penalties would be okay? So let's go to the matter of characterization of minimax rates in statistical risk problems through Shannon capacity. So since Shannon capacity is so closely associated with the communication problem, let me, for this act, let's disassociate those quantities a bit, right? Remember that there is an information capacity, C, that any family of probability distributions would have. So for the statisticians in the room, when you hear an information theorist say a channel, it just means a family of probability distributions, your bread and butter, okay? They're the same thing. We might use theta rather than x, right? They might be structurally different. Maybe from a single theta, you get a whole sequence x, as opposed to from a string of x, a single y. Or I said it wrong. From a single theta, you might get a whole string of y's, as opposed to a whole string of x's producing a string of y's. But the same information capacity, the maximum over distributions on the input random variable theta of the mutual information between theta and y. So in the statistical setting, that might be called a prior, and you're maximizing an average case of something. The communications capacity, CCOM, soon to be called C, long ago called C by Shannon, is the maximum rate of reliable communication, rate being the number of message bits divided by the number of uses of a channel, where an encoder would choose what to be sending from the set of messages, and a decoder would be decoding the message and doing so reliably, and the largest value of that rate, the supremum of those rates, would be Shannon's capacity in accordance with his theorem. But it goes on, because in data compression, there's also a fundamental role for the information capacity. So in data compression, we'll come back to it, DPQ plays the role of the redundancy of data compression. Okay? After our initial excitement of knowing that the entropy is the minimal expected code length, now let's get down to brass tacks. You don't know the distribution. You got a game to play. You got a family of possibilities for that distribution, P of y given theta. You have one coding distribution, Q, and your loss is the expected difference between the code lengths, which is dpq. So the minimax redundancy is the minimum over Q of the maximum over theta of that. And now we've set it up as a Wald-style decision problem. Minimax equals maxi-min, as known from the 1950s, and reiterated in the 1970s by Gallagher, Davison, Leon Garcia, Ryabko, and others, telling us that the minimax redundancy is the information capacity of the statistical family. So for the problem of data compression, when you play the right game, which is the game of making your redundancy small, then the relative entropy is the right measure, and its minimax value is the capacity. Now, for the statistical setting, we could take a narrow sense by choosing only Kullback-Leibler, but I already hinted at the fact that the loss structure for many different types of loss are asymptotically similar. And so when we talk about statistical capacity, I'm not going to be concerned about constant factors. I'm just going to be concerned about rates. And I'm going to be thinking about those situations where instead of the parametric rates, like 1 over n times Fisher information, instead we get non-parametric rates, like 1 over n to the 4/5, associated with certain smoothness of the function. So in those situations, we typically still use a loss that might come from a choice of distance based on the distributions. So one could have the squared Hellinger distance between the distributions and define one's loss by the associated distance between the parameters, or likewise for Kullback. And the Wald statistical risk of a procedure is the expected loss. That's a choice of your procedure. That depends on your procedure, and it depends on the parameter. And the minimax risk of Wald is the value associated with that procedure that would minimize the maximum risk over the parameter set. If we envision that you're doing this based on a sample of size n, we could index that risk by n. And we're familiar in information theory with the way that statistics tells us the fundamentals of what's possible for any procedure, and that's true here too. We want to say no matter what estimator it is, what would be the best lower bound that we could have on the minimax risk and best upper bound asymptotically. Now, there's a long history of converses connected with the use of mutual information, with the inequality of Fano playing a prominent role. And that happens here too. And it has been borrowed into statistics by some fine scholars, Bragamoth and Hesminski and Berger. And being not as familiar with the use of the information quantities, they tend to work with it in a form where they're looking at Kullback distances between pairs of distributions. But I'm getting ahead of myself a little bit, but I'll finish what I'm saying. It turns out that it's the mutual information that asks for the average distance in relative entropy of members from their centroid that really matters. And what do we mean really matters? Well, what one heads towards in the work of the authors I just mentioned suggests a fundamental role for Kolmogorov metric entropy in resolving minimax rates in statistical problems. But because of the particular uses of inequalities implied by Fano rather than the original Fano inequality, these works tend to force the mathematical statistician to find special cover properties of whatever class of functions he has, which maybe, there's another paper for each function class you want to look at, but if there's a sweeping way of characterizing what's going on, we should know about it, even if it means a few less papers. So the Kolmogorov metric entropy, no accident that he calls it entropy, asks about the maximum packing number, maximum log cardinality that you can have so that the distances between points in a set are at least epsilon. And let's suppose we have a loss that is both locally like a squared metric and locally like Kullback-Leibler, the natural squared metric being Hellinger. Then a theorem that where Yu-Hong Yang did it in his thesis, and we had a paper together in the Annals of Statistics, as did Hausler and Opper, who built upon the earlier form of ours. They were quicker to print, but it was, they were still motivated by what Yu-Hong and I had gotten. And the result says that these favorite quantities of ours are all asymptotically the same. The minimax risk, the information capacity rate, the metric entropy rate, but you have to choose an epsilon. You choose it so it's at the appropriate precision, epsilon n squared. And by these wiggles, I mean the ratios are bounded by constants asymptotically. That's a nice take on it. You won't in any of these papers find literally that rendering. So I should thank John Lafferty, who in this room just a few years ago gave a tutorial. And in the tutorial found that way of expressing these results. And I liked it and choosing to do likewise. Because it rather than just saying, I mean, what it usually boils down to is you pull out, a knowledge of the metric entropy and you solve for the epsilon that matches these two, and now you know your minimax rate. But the method of proof is showing the relationship to information capacity, actually through the data compression form, not the channel form. It's the same quantity, but that's the way it arises. Okay, I'm going to move next to the adaptive finite sample stuff, but any question about the minimax asymptotics? Typically what happens here is like you look at a function class like functions on a unit interval whose derivative of order s has some norm, less than 10 or whatever, okay? Then the log cardinality of the best packing or of the best cover in the Euclidean, in L2 distance between functions is of the order of 1 over epsilon to the 1 over s. In higher dimensions, it's a d over s. And then you can just say, oh, okay, now I need to match that divided by n with epsilon squared, and out pops the familiar convergence rates of nonparametric statistics, which are fractional rates. They're 1 over n to some power between 0 and 1. Getting better as you have more smoothness, getting worse as you have higher dimensionality. Okay, so now let's transition. We're going to put on a different hat. Because the hat we want to put on now is, what should we be doing in the way of statistical procedures? There's a lot of effort in statistics in trying to formulate a right way of thinking about how to proceed. And I think that information theory can be helpful here as well. And in this, I'm championing the approach that Jorma Rissanen has made a career out of in saying, well, it's obvious, just minimize the total description length. And I'm highly sympathetic to that, but I want to connect it up to statistical properties, not just compression properties. But let's start with compression. So the uniquely decodable code lengths, as any information theorist here knows, are given by integers that are non-negative, and the sum of 2 to the minus those integers is not more than 1. For any such set assignment, there is a uniquely decodable code, indeed an instantaneous or prefix condition decodable code with those links. So if we set q equals 2 to the minus L, we could think of L as log 1 over q. It's deeper than that because the Shannon code for X based on Q uses the values of the cumulative probability of Q. You use its values in bits to that precision, and that's the code. So when information theorist says, I'm going to code using that distribution, it's very literal. It's the bits of the CDF, and there's a choice of order. If you leave it in, if you sort, you have the Shannon result that you're always within you can have a code length which is the rounding up of an integer, so you're within in 1 bit of that value. If you don't sort, there's the Gilbert-Moore result that says that you can be within 2 bits. We're talking about long strings, so we don't care about 1 or 2 bits. Now, but this means that to an information theorist or to a statistician who embraces the notion that you want the best summary of data, it gives probability an operational meaning. We hear all the time about frequentist versus subjective probability. I think there's also operational probability. By their fruits you'll know them. By what you do, you reveal your probability assignments. And a lot of activity can be thought of. I mean, any communication, even now, if you're understanding, there must be some underlying distribution governing my communication. So a probability distribution is revealed by how you communicate, how you code. But this leads to nice games where we ask things like, okay, there are lots of different distributions. Maybe I wish I had coded using P, but I didn't know to when I coded using Q. So I'll have a regret. The difference in the code lengths. Its expected value, as we hinted at earlier, is dpq, the relative entropy. And its non-negativity is what tells you that the idealized code length. I see I'm merging 2 files. I'm using y sometimes and x sometimes. So when you see that, that means x equals y. So the Shannon idealized code length is log 1 over p of x. It has the shortest expected code length. Huffman code would be literally optimal in expected value, but we don't care that much about expectation to do the complicated Huffman trick. The Shannon or Gilbert-Moore approaches which give you code lengths directly related to log 1 over probability are more to our taste. But we don't know p, so we can't code that. I mean, we're statisticians now, not probabilists. We don't know the distribution. We're trying to learn it. So Rissanen began the process all through his career, it's what the dot, dot, dots are for, of describing various incarnations of what he calls the minimum description length principle. And it was fun for me in 1981, having just joined Tom Cover at Stanford, and talking about my interest in finding principles that could be the Unke-Gerd tough statistical learning problems. He wrote down on a yellow sheet of paper I still have in my office somewhere, basically that formula. And at that point, he didn't remember that he had also had a similar conversation with Jorma in the mid-'70s, and he was not aware of Jorma's papers on this. So there was some initial proceeding independently, although belatedly on my part, in developing an understanding of that, and I've enjoyed making contributions to that as well. So but it's a statistical measure of complexity. So when we talk about MDL, its purpose is statistical. Okay, its purpose is not information theory per se. It's to learn statistically from data. Its motivation comes from asking for the shortest description. So the earliest incarnation of it is you say, well, one way to describe data would be to first describe some coding distribution Q using L of Q bits, whatever that is. It just has to be Crass summable. And then once Q is described, I use log 1 over Q of y bits to tell you y. And, well, as long as I'm doing that, why not find the best such? Any Q would give me a valid such code. We'll find the best such. That'll be at some Q hat or P hat, we'll call it, that achieves that minimum. And so now typically in certain realizations, you'll have a parametric family that you have. If you're doing it by these 2-part code, you might well have discretized the parameter set and described possible parameter values to some precision. It turns out that 1 over square root of ni is the right precision. Or maybe you're trying to learn some functions, and then there's the issue of, well, how do you discretize the parameters of that function, or do you do it by some Kolmogorov means? But or either by his metric entropy or by his complexity theory. So that gives a lot of freedom for how you're going to describe possible coding means. And then the question then is, what will be the behavior of the estimator that achieves that minimum? Now, I want to make a distinction that there really are two aims, and both are important. In data compression, you're looking at one string, x1 through xn, and you want a choice of a queue that compresses that one string well. Those that have been involved in universal data compression, you know that what you really ought to be doing is some sort of coding based on a mixture or some kind of sequential updating of conditional distributions based perhaps on estimates of the parameters from the past, which can implement such Bayes mixtures. And then you say, well, when it comes to future data, you're going to keep doing that. As you get more data, you're just going to keep updating. But I think that there is a legitimate statistical interest in saying, okay, I've got a certain p hat right now. How good is it going to be in the future? How good is my p hat? So what you want is not just good compression on the training data. You want to be able to say of your p hat that it will generalize well to future data, x prime. So we want log 1 over p hat to compare favorably to log 1 over p when evaluated at x primes. Both are of interest. One is more directly the compression problem. The other captures the spirit of what you want of a good statistical procedure. There's comments here about loss. Here it is. So we have the Kullback loss. And I mentioned Hellinger. Closely related to Hellinger is 2 times log 1 over the Hellinger affinity. It's 1-to-1 with squared Hellinger distance, and is the quantity, as in a Chernoff exponent, that most directly gets connected with relative entropy and with the arguments that we're about to give. But if you want to think of it as squared Hellinger, feel free, and that's why I wrote it as a d squared. Both this Bhattacharya-Hellinger-Vignay Chernoff type divergence and Kullback-Leibler share the property that with IID distributions, it's just n times the individual distance. Also, as I mentioned earlier, there's always such relationships. D squared is less than D is less than 2 plus the constant times D squared if the log density ratio is bounded by such a constant. Okay, so how do we analyze minimum description length? We want to analyze it both in its redundancy and in its statistical risk, and we want to see to what extent are the same tools arising. So in its redundancy, that's the expected difference between its minimum 2-part code length and log 1 over p. And that expected minimum, a clean, simple upper bound, is that an expected minimum is less than a minimum of expectations, less than or equal to. And when you use that, that identifies the index of resolvability as an upper bound on the redundancy. The index of resolvability trades off the error of approximation of p by members of your families, trades that off with what? What's the right price to assign to some approximator? What this says is that the data compression motivated price is its complexity divided by sample size, where complexity should not be thought of here as simply log cardinality. That would only fit if you knew what function class you wanted to have a minimax result for and you were locked in. You know the truth. Don't confuse me with how the data suggests that something simpler is better. But if you want to have an adaptive procedure, then your measure of complexity should be varying, and simpler things should have shorter descriptions. And the appropriate trade-off, the fundamental trade-off I would maintain that governs statistical adaptation and data compression is this trade-off between complexity relative to sample size and Kullback approximation. And with a slight modification, it turns out that that same quantity upper bounds that expected divergence, where, yes, we would love it to be Kullback-Leibler, and in certain special cases, like bounded density ratios, you can get that. But one of the spirits of results I like to try to shoot for, though it comes at a slow pace, are results where you're not putting down any assumptions about the structure of the families at all. You know, you want this, you don't want to say, now, if I have a log linear model, or if I have a, you know, a generalized linear model, or if I'm doing, you know, this type of regression or that, then I'll have another paper for it. And, well, I don't mind more papers, but what is the underlying principle that can be specialized to each of these cases? And it says that the statistical risk is governed by that same index of resolvability. And so now there are special cases. What are the traditional penalties looking like? So one would be a number of parameters over 2 log n, or other penalties that are based on dimensionality of the parameter set. This is the one that corresponds to the appropriate balance for smooth families. There would be a role for Fisher information in the literature that, you know, explaining it in greater detail. Non-parametric, you could use this to adapt to different function classes. There is an idealized one, the one that Tom Cover wanted me to be focusing on more to the exclusion of the others, and that was just use Kolmogorov complexity, because it's the shortest length description of a Q amongst, you know, all computer programs on a universal computer. And it would automatically, by this inequality, achieve minimax optimal rates simultaneously in every computable subfamily of distributions. All those you know and all those not yet, you know, written about. Of course, you can't do it, but it's nice to know about these ideals. Now, but for risk considerations, you can't just look at the redundancy alone. You have to ask about this connection between the behavior on the training data y and on future data y prime. So in empirical process theory, people study such empirical departures. Maybe in place of the quantity on the right, you might put a population counterpart like a mean, and then you have an empirical process that describes the difference. And typically metric entropy conditions are used to produce uniform controls on minima of such empirical processes. What is the just right control for statistical and information theoretic purposes? Well, one is one-sided. Who cares about the other side, the supremum here? It's only the inf we need. And the other is, it's not according to a particular metric or a particular epsilon. It's the complexity. And it turns out, here's a simple inequality. If you choose the right population counterpart up there, the expected infimum of this discrepancy plus 2 times any Kraft-summable code lengths is bigger than or equal to 0. And the proof just replaces the infimum with a log of a sum of exponentials, and then out it pops by using a Chernoff bound. So it should get you wondering, well, how should we be doing empirical process theory then? Are we doing the right thing by focusing on particular function classes and demanding, you know, some that the L's be log cardinalities, and that the discrepancies be uniformly bounded by constants? Is that what's statistically essential? It may fit certain mathematics of approximation theory, but is it statistically essential? Well, from that inequality, in fact, all you do is say, well, if the expected infimum is bigger than 0, then take, in place of that infimum, put the Q hat, or the P hat that's the minimizer, and then put the population counterpart of the discrepancy there on the other side, and it's what gives you this risk, less than redundancy, less than resolvability. And these are finite sample bounds, and they hold for with constants of 1. These are not wiggles. The constants are 1. And the independence isn't really needed. I chose independence in the way I'm writing it for having fewer n's running around, but you look at the total Bhattacharya divergence and total Kullback divergence when dealing with dependent processes. So, good. There's a shortcoming, though, and that's that was about, since those L's had to be code lengths, I had to have just a countable number of possibilities that I was minimizing over. Okay, now as information theorists, sure, we can have fun dreaming those up, but do we really want to tell someone, no, you can't use that L1 penalty, you got to discretize first? No, you know, we like to be able to explain what type of penalties are going to be effective. So the likelihood penalties arise in practice in myriad ways, through the number of parameters, through roughness penalties, as I mentioned earlier, coefficient penalties, as I just mentioned, like L1 norms on coefficients and a function expansion, through Bayes maximum a posteriori estimators if W of theta is a prior, through maximum likelihood where the penalty would be a constant, through MDL, which I've already been talking about. All of these have this penalized likelihood form, and except for MDL, you're not thinking about having a discrete set there. So, I mean, even the number of parameters case, you're still thinking about a continuum of real parameters, or at least an interval of parameter values for each of the different parameters. So you want to be able to say something about what happens if you do such a minimization over a continuum, or whatever space these Qs are in. And the question that is the right one to ask, notice something. If I do this minimization, I could put the true P of y inside the log. I don't know what it is, but it wouldn't change the minimization, because that's the log of a ratio is the difference of the logs. So, but once I put it there visually, just for analysis' sake, then we have that's the sample counterpart to this population minimization. So a very appropriate question is, to what extent will the behavior of one's procedure, when you use a p hat that achieves such a minimum, produce a risk bound governed by the corresponding trade-off in the population between error of approximation and penalty over n, whatever that penalty might be? Some penalties aren't going to be enough, and you won't get such a connection. Some penalties might be overkill, and you get it, but you wish you'd had less penalty, because then you'd have a better risk bound. So, be fun to, if someone could prove that this is kind of an if and only if, but at least it's an if. We have a condition that guarantees for, you know, whatever, use your favorite class of penalties, for what multiplier on them or what form of them will work. And it is not, I mean, a lot of papers that try to show adaptation properties boil down to people saying, well, let's see, in this function class, I got this metric entropy, and in that one, I got that one, and I do some, you know, I appeal to empirical process bounds across all of them. Well, here is an attempt to distill the essence. Suppose you get one of the smart people in this room who cares about, you know, the mathematical statistics and information theory to take your favorite penalty. Maybe you're the one who can do it. Take your favorite penalty and see if you can find a countable collection that has of Q tildes that have this following property: that the penalty is bigger than a minimum of twice a code length plus this distortion, this difference in discrepancies at Q and at a representer Q tilde. I chose not to get too specific here too quickly. And if one is found, then you know that you'll have this risk bound, and again, it'll hold with a constant of 1, and it'll hold for whatever was that penalty, even if the Q is now varying over some continuum. It's like, you know, all regression models with all real valued coefficients with some penalty on the sum of absolute values of the coefficients. Or a regression model with k parameters, and you do least squares on that k term subset, and your penalty is just depends on k. you'd like to be able to say, all right, will there be hidden under the hood of the car a appropriate countable set? You could kind of call it a cover, but it's not a cover in the traditional Kolmogorov sense. It's a variable complexity, variable distortion cover. And then we will make a distinction between those penalties for which we can show that they are code-length valid and those that are risk valid. We might be lucky and have the same penalty satisfy both properties, or we might not. So some penalties might be good for compression but not for risk, or vice versa. So far, we tend to find that they're good for both. So the difference is, and this gets to the heart of how you can think of minimization over a continuum as still being a valid code length. Okay? Here, we already argued, it's most clear-cut in the discrete x case, but that these are valid code lengths for x if you're optimizing over a discrete set satisfying Kraft summability, because that's the length of a description, so, you know, the Kraft-McMillan inequality tells us it has that summability. So if I can verify for some other penalty minimizing over a continuum that the resulting minimum penalized log likelihood is bigger than or equal to this, then that value up there is also Kraft summable. So even though you did a minimization over, you know, all the real parameters, if the result of that minimization is provably greater than for some, you know, code lengths L in a minimization over a countable set, then the top length is also a code length, not just the. It's just a matter of, any, you know, of an ordering, right? If some L is bigger than or equal to these L's of X, then they will also be Kraft summable. So, and that's equivalent to saying, you know, can you ask an information theorist to, or a mathematical statistician to find for you, for your favorite penalty, a property that for every theta there is a countable, well, there is first a countable theta tilde set, such that for every theta there is a representer theta tilde, such that your penalty is bigger than the description length plus the log ratio of likelihoods. So this is the core of the variable complexity, variable distortion cover property. If you have such a penalty, then it will turn out to be compression valid. And this is the link between the uncountable and countable cases. The link that you need for the risk properties is you need to subtract from those log ratios population counterparts. Wouldn't it be grand if you could subtract Kullback-Leibler numbers? You probably can prove such a relationship, but for getting the risk conclusion, I only know how to do it in the degree of generality using the Bhattacharya-Hellinger style population counterpart to the log likelihood ratios. So if there is such an inequality, then it turns out that this, the statistical risk property will hold true. Because as we already discussed, the expected minimum of the second quantity is bigger than 0. So by that inequality, the expected minimum of the top quantity would also be bigger than or equal to 0. And so evaluating at theta hat and pulling the loss to the other side gives the desired risk bound. So that's an abstraction. And this is in the same spirit as what Ben was talking about in the previous lecture, where he's saying, what are the kind of, what are general principles that we can use that capture results that we see when we specialize in many different cases, and that can be a tool for not just reproducing such, but for new cases. So, for example, if you take regression or log density estimation problems where you have some basis expansion, your F's are linear combinations of some functions in some basis, and your penalty is the sum of the absolute values of the coefficients with some attention to the detail of what weights to give those coefficients. Then the question, then that would give rise to the lasso or basis pursuit algorithm that both of the previous tutorialists explained. And then the question is, well, okay, what lambda makes this a valid penalty for compression or for these risk purposes. And what does this look like? So when you're doing regression, you're doing something like what you see in the middle here. And the claim is that it's code length valid and risk valid for the very same lambdas, these. This too just comes from ensuring that your basis functions, that you can flip signs on them, because the argument for this has to do with choosing positive coefficient values, so you might have to double the size of your dictionary P in order to have, and that's the same lambda that's been mentioned previously this afternoon. And that precise constant makes it work. Now you might wonder, well, what if you don't know sigma squared? Then, and notice I scaled things in a particular way here to make this come out clean like that, where I did a division by sigma on the penalty. And if you put in the appropriate log likelihood component from sigma squared, and you minimize this over sigma squared as well as over thetas, then it too will have the risk validity. And it's fun to write out the form that sigma hat has. And in the conclusion, when you specialize it, says that an expected squared distance between your estimated function and the true function, this is because of the Gaussian nature of the noise, so the Bhattacharya divergence, like Kullback-Leibler, is just a multiple of L2, is given by an infimum of between error of L2 approximation and L1 norm. And that allows you to specialize to the case that what if the truth has a certain L1 norm that gives you a 1 over square root of n rate times a log factor, but even if you didn't, and it would give you other rates that interpolate between. Okay, there's some fun about how that's done. Maybe I'll briefly mention it. What do the representers look like this? We never have to actually use this countable collection. We only have to show it exists, right? And I don't need the representers in practice, just need them for the proof. So get your representations by following the time-honored tradition since Shannon of picking out a representer at random. Pick the G1 through GM using probabilities proportional to the coefficients of the f theta that you're trying to represent. It will produce in expectation the property, the inequality you want, so there must exist such an f tilde for which it's true, the random coding argument. Okay, so that's the end of Act 2, where our summary is that Shannon capacity determines limits of statistical accuracy, and that we can do adaptation by penalized likelihood, and that information theory tools provides a means by which to assess which are the types of penalties that would permit that to be true. And the risk is controlled by this trade-off between Kullback approximation and penalty relative to n, but only for those penalties, at least as shown here, that have an under-the-hood variable complexity, variable cover condition verified for it. So that's the summary of Act 2. We're going to move next to the practical channel coding. Any questions on information and statistics? Harry, you got one, don't you? Oh, no, that's not a question. He's tenured already. He's not buttering up.
I'm tenured, so I'm not afraid. So let me ask a question. So you pick lambda n equal to square root 2 log 2p divided by n.
Yeah.
So, but your livelihood part is divided by 2.
Yes.
And then in some sense, your penalty is like square root 2 times square root 2 log 2p divided by n.
So he's.
What David was suggesting, this volume was even smaller than square root 2.
Okay, so. Okay, David probably has me beat by a factor of 2. I'm honored. Okay. Yeah, there is this factor of 2 that you may have caught in that story where if you want the degree of generality, it appears that some such is needed. If you work hard in special cases, you can avoid it. Any other questions on information and statistics? Yes?
I wonder if you can say a few words about, you were talking about the discrete case and the continuous case. Your results, you say, the sort of equivalent.
Yeah.
But for those of the basic statistics, we know that there's a fundamental problem with the trying to seek for this non-informative price, the discrete parameters.
Yes.
Uniform, pretty much everybody can accept that's okay, but once you do continuous, you run into all sorts of problems. It's not inherent to the amount of transformation.
Well, there are all kinds of fun questions there, and I've had fun with some co-authors like Yang Feng and Bertrand Clark studying some of the properties. So you can ask questions like, well, what would be that least favorable prior which would produce the minimax asymptotics for the total cumulative Kullback-Leibler risk? And the answer is the Jeffreys prior, the prior proportional to square root determinant of Fisher information. But you get a finite minimax value only when that's normalizable, only when Fisher information is integrable. So if it's not, then you're playing in a minimax playground you shouldn't be in because it's going to be infinite anyway, and you got to put on your adaptive hat. And when you are trying to be adaptive, it is harder to be definitive as to what prior you should use. But this type of thinking does help us because we can use those types of asymptotics in understanding, given that we all should be using Bayes procedures, it would be inadmissible to not be using something close to them, then what will be in repeated play? What will be their large sample risk properties, and how is it related to our choice of prior? And the information theory helps provide such a bridge between the Bayes and frequentist perspectives. It enables you to say, here will be the cost and my risk of having not put enough prior attention to this part of the parameter space, if that's what governs the data. So that's just a glimpse of some thoughts on it. By golly, it's not an easy problem to have a kind of default procedures, to put in, whether they be Bayes or frequentist. Have I addressed some of your interests? Good. All right. So this is fun. I would just come back from a trip in 2008 to Hungary and to France, talking about the things I've been talking about. One was honoring Imre Cizar on the occasion of his birthday in 2008. And I come back and I'm jet lagged, and I'm a director of graduate studies, and they have a parade of master's students coming in, and they all want to study, they all want to learn statistics so they can transition to doing finance. About 50% of the master's students coming in, that's what they say. So I got one coming in, and he says, my training is in electrical engineering, and now I want to learn statistics so that next year I could go on for an MBA. And I said, well, it's a fine, time-honored thing to study finance, but while you're spending a year at Yale studying statistics, please put on a more general hat and think about what your statistics could be useful for in other areas. Take, for example, electrical engineering. And I'm trying to mention a number of ways in which statistics is useful in electrical engineering. I was trying to describe LDPC codes, which is not an area I'm an expert in. And we all, most of us know what they are when we're lucent. And I wasn't so lucent, and I described it incorrectly. I said that you have it's a linear code, and that the coefficients of linear combination are sparse, but the generator matrix is full. And that's backwards, right? In LDPC coding, it's the generator matrix that's sparse, and you fill up the coefficient vector. But as I'm saying it, I thought, well, I got that wrong. Not worth trying to correct it here. And it might work. So I set to the task, and within a few days I had myself convinced that, yeah, this would work. And that, it's more to the taste. I didn't want to talk about finite fields, and I didn't even mention that aspect. These were just reals as far as that student was concerned, and as far as I'm concerned. So what I want to talk about is achieving Shannon capacity with power constraints by a regression setup, borrowing ideas from statistics and from information theory, and using some of these tools. So the formulation is that we have input bits. I mean, this is just the standard information theory setup at first. We have input bits U1 through UK. So there are 2 to the k possible choices, and each is equally likely to come as an input to be a message to be encoded. It's encoded by a string x1 through xn from the input alphabet of the channel, p of y given x. And then out of that, you receive y1 through yn, and you produce the decoding, u hat 1 through u hat k. The rate, as we said earlier, is the number of information bits divided by the number of uses of the channel. Shannon tells us that the maximum, or the supremum of such rates that have high reliability is the information capacity C, the maximum of the mutual information between the input and the output. And that mutual information is the Kullback divergence between the joint distribution of x and y and the product of their marginals. It's a measure of the hypothesis testing exponent for dependence versus independence, which is the relevant test for the decoder who's trying to decide which x was sent, that one being dependent with y and all the others being independent. The reliability requirement is that you want to be right with high probability, and we're dualistic in information theory about this. When we set up this problem, we say it in terms of block error, but when we set it up allowing distortion, we would tend to think instead of the fraction of mistakes, and wanting the mistake rate to be small. And it turns out that it doesn't change the capacity to care just about having a small fraction of mistakes, as opposed to a block error probability. And there are ways to go from one to the other. In the Gaussian case, you add the constraint that the average squares of the x's is not more than the power p. I'm going to relax that in a way that works for the practicality. Instead of demanding that every length-in code word satisfy that, I'm only going to require that averaged over the 2 to the k messages. Okay? You can convince yourself that that doesn't change the capacity. Okay, so that but it does mean some of your code words might be of higher power. In the long run, if you're blocking this in and then the next in and the next in, the long run average power use will still be not more than p. So it's kind of, you may need a little bit of bursty power capability, but in the long run it has to still average to p. A channel is that y equals x plus normal noise of variance sigma squared. I'll use z for other things, so I'll use epsilon for the noise. The capacity we know is half log 1 plus signal to noise ratio. The maximizing distribution on x in accordance with Shannon's characterization is the Gaussian of variance p. And in the study of the converse, we know that if you want the rates near capacity, you know that your code words have to be mostly on an appropriate radius sphere in Rn and be well separated. So this problem of practical solution to channel coding is studied in the book by Conway and Sloan, related to the questions of optimal sphere packing and whether that can be done practically. So here's a one-page dense attempt to say a few things about relevance and history. So though many study the binary symmetric channel, and it's a nice prototype, it's generally acknowledged that the real channels of communication across wires or through electromagnetic radiation through the air, after some good work, reduce to the Gaussian noise channel. So even if they're in continuous time under certain bandwidth constraints, it still reduces down to this model. And a nice review of a lot of the overall issues is in the 1998 IT paper by Dave Forney and by Ungerbach, where they deal with modulation, coding, and shaping for the Gaussian channel. Now, we're in a kind of interesting history within our field where for years we sought the holy grail of a mathematical proof of a practical scheme, and were jolted in the 1990s by empirical demonstration that LDPC and turbo codes did the job. And there was even back and forth. Is this information theory? Is this legitimate? Is the problem solved when we have empirical verification? You know, Xiaoli, you might find that interesting. You're talking about, I mean, what the simulation are they doing? Monte Carlos. So Monte Carlo tells us that LDPC is working. Can we trust them, Xiaoli? You know, have we run big enough Monte Carlo sizes? And what will happen if the reliability requirement, you know, gets more severe as we go to faster computers and more memory? Do we know it'll scale? Do we know that LDPC will continue to empirically work? No, we don't. Now, there's some good hints. Nice book by Richardson and Urbanki gives some framework for studying it, and I had a good conversation with Rudiger about it. I was trying to say, look, there's some aspects where you've got some theorems about it, but he says, no, there's simplifying assumptions that give rise to a particular path of analysis, but it does not come to a theorem that these methods are working. With certain exceptions, and that's by Luby and Spielman et al. In the study of the binary erasure channel, where we do, and certain closely related channels subsequently, people have shown theoretically that they are practical and achieve capacity. But then there's the very recent, now highly recognized, award-winning paper by Erdal Arakan, where he invented polar codes, which was nicely surveyed yesterday morning, where where these are codes that create simplified channels out of more complicated ones, where there's work in doing a simplification. Once you've done it, then coding becomes easy. And Emmanuel Abe, who is in Teletar's group, is studying, in part with me, adaptation of polar codes to the Gaussian channel case. There, see, the polar coding argument began by thinking about binary input channels where capacity is achieved by a uniform distribution on the inputs. But you can go to higher order alphabets and even to multiple access channels, and indeed that the alphabets of larger size can best be thought of by specializing the multiple, if a single user cases, by specializing the multiple access cases. And we're having progress some adaptation of those results to the Gaussian with appropriate signaling ideas. So I like those too, but I want to talk about this regression method. So the method I'm going to talk about here is different, and prior knowledge of any of the above is not necessary to understand the essentials. So we're going to have a sparse superposition code. So we're going to have, let's go to the middle, this matrix X, this dictionary, which has n rows and big N columns. Big N might have also been called P, but P has already been way overused in this talk. I just couldn't come to using P for the number of columns. And it's filled with independent normal 0, 1s. Now, so there is a random, in the proof, we are taking an average over the random dictionary. I'm not giving any one explicit dictionary for which the claim holds. However, because the algorithm for decoding is fast, you have the fact that you know with high probability it'll work, and two, you can do some Monte Carlo to check. So it's not the same spirit as filling in a code book of size 2 to the NR and keeping your fingers crossed and never being able to compute it. Now, the means of encoding is actually very simple. You take those input bits, and you're going to, on the basis of their values, choose some places to put non-zero coefficient values. We're going to say that the number of those places is L. I couldn't bring myself to use K, which is common in compressed sensing and support recovery problems because k is the number of information bits. So, we get stuck in those sorts of things. And the code word is x beta. So it's the linear combination of the columns chosen. And you receive y equals x beta plus epsilon, a statistical linear model. And the decoding, we will explain. The rate is if you were allowing all such sparse subsets, the number of information bits you could throw in would be the log of the number of subsets of size L out of N. And the reliability for small alpha, we look at the probability of a fraction of mistakes on the beta hats being more than some small amount. To correct those small fraction of remaining mistakes, we embed our sparse superposition code as an inner code with a Reed-Solomon outer code. In this respect, it bears similarity to things Dave Forney did around 1960, but he had separate such concatenated codes for each of many uses of small Shannon optimal inner codes. In this case, it's different. What's going on is, I'll explain best in another minute, but there is a outer code rate, 1 minus 2 alpha, and if alpha is small, the overall code rate is still close to the inner code rate, which we will want to be up to capacity. So the analysis is simpler if we use partition superposition codes. So the partitioning consists of requiring that there is one non-zero in each section. And this makes the encoding really easy. Suppose that these section sizes are powers of 2. So B, the section size, big N divided by L, is a power of 2. Then I can partition the input bit string into streams of length log B and read those as numbers, telling me the address of which column is going to be given a non-zero value. So you just read off from that little segment of the input bit stream which of the columns is going to get a non-zero value. So there's one non-zero in each section, and and then we let J1 through JL be the indices of them, and that corresponds to U, and that tells you which are the non-zero coefficients. The matrix also splits into such sections. The rate, now there are, of course, B choices from each section. There are L sections, so you have B to the L code words altogether, or the K is L log B, and that gives the relationship between the fundamental parameters of the problem. It's like if you set B equals N to get a feeling for what kind of size I'm thinking about, then the number of sections L is like a NR over log N. I'm thinking about it right now, so I'll mention it. This bears similarity to issues in compressed sensing, but we see the role of the constant there is precisely given by the rate, and so you want the best constant to be the Shannon capacity. So the compressed sensing capacity in a certain framework is the Shannon capacity. So we mentioned reliability already. So what happens here is the Reed-Solomon code is working on the J1 through JL. Those J's take values in 1 to B, which is a power of 2. You represent them in the appropriate finite field representation, and those are the symbols of the outer Reed-Solomon code. And what that outer Reed-Solomon code is doing is guaranteeing at least a certain separation between the choices that are sent. If I don't have it, then you could have a choice where I've got two code words and they differ, say, in only one section. Those are going to be hard to disambiguate. But if I have this outer Reed-Solomon code that is maintaining a maximum distance separable, maintaining the best possible separation between those sequences of labels, then that glue's just right for producing the required packing properties. Power allocation. There are two choices of note. One is to use the same power, P over L, for each of the terms that are non-zero. So what we do is we set the coefficients to be square root PL, where the PL sum to P. We could use constant power. We could use some scheduling of powers that drop off as the section index increases. We might have some compromise between them that levels the power. And what happens is that if you study the behavior of least squares, Anthony and I have submitted a paper last year where we say you can get up to capacity by least squares with constant power. But by the iterative fast schemes we're using, we can't get that to work. It stops at a cutoff rate below capacity. But if we use variable power, and multi-user information theory specialists will recognize this power allocation. This is the appropriate power allocation for rate splitting for the sum rate and multiple access or broadcast Gaussian channels. But what's different is that the choices of our parameters here are such that this is not decaying very rapidly. It stays between 1 and e to the minus 2c as L goes from 1 to L. And we'll explain how things are working. So here's a plot of what the power allocation might look like. What's going on is that we're going to have an iterative decoder. If we were doing it by Cover-style rate splitting and successive decoding, we would say, let's just decode the first section first. Okay, got that one, now the next one, now the next one, and so on. But that requires exponential size sections to get the reliability you need. Here we're going to get the reliability by looking for terms that stand out across the whole spectrum of sections. And early on, the early steps, they'll tend to be more from early on. And then as you take more steps, you'll tend to decode ones from later on in the section index list. So we contrast two decoders. I can finish in 5 minutes. One is least squares. That would minimize the error probability with uniform input distribution. And as I mentioned, we've submitted a paper that says that's reliable for all R less than C and characterize the error exponent. It is of the form e to the minus some multiple of c minus r squared if r isn't too far from c. It's not the Shannon-Gallagher constant there. Maybe it is, but at least our proof doesn't reveal that constant. But it is at least of that right order. It's exponential. And the same will be true of our practical scheme. We'll get exponential error probability bounds in contrast to the e to the minus square root of n bounds of polar codes. So it's going to be fast and reliable. Yeah?
Can you clarify what you mean by these squares?
Yes. So excellent, David. Not over all reals. So because then you could do that. What least squares would mean here is over the assumed form. So if you could do least squares where there was just one non-zero in each section and with the value that you know it would be, if you could do that, then you would have these reliability properties. So that was studied as an intermediary in understanding whether the scheme has potential. We talked about it at a gathering you were at a year or two ago. And you asked questions at that time about the practicality, and that's where Anthony and I have been taking it. So what is the decoder? So it's basically, there's a class of schemes for problems with sparsity constraints. You have the iterative schemes where you try to build up a sequence of terms. So you have like the relaxed greedy algorithm theory that initiated by Lee Jones, which if you have an L1 constraint, there are papers from the early 90s which gave risk understanding for and computational understanding of what is achieved for such. But here, it's not about the type of risk we were talking about before, where we just wanted x beta to be close to x beta star. We want the betas close to the true betas. So it is more, a need to get the right terms. We have drawn our columns independently, so they tend to have near pairwise zero correlations. So you gotta hope for that. But now what type of procedure? Well, they're like the Lee-Jones relaxed greedy algorithm. You want to say what new terms to bring in, but you can't be to go for too much too fast. So the way we do it, because we're not after some convex combination, we don't want just some L1 constrained or L1 penalized solution that'll take us to some convex combination, leaving the problem of finding which vertex you're near. Instead, we want to move amongst the vertices. The key is don't commit too fast. You set a threshold. So step one, compute the inner product of y with each column of x. See what you're above a threshold. Set the threshold in accordance with what will make the false alarm rate suitably small, which is standard normal theory. Form an initial fit as the weighted sum of the columns that are above threshold. Iterate. So in this respect, this is a lot like, say, forward stepwise regression, also called orthogonal matching pursuit, also called L2 boosting. Okay? Goes back to 1960 as forward stepwise regression. But instead of doing projection onto the terms selected, we already know what coefficients we want there. So we're just making the choices of the next set of columns so as to, by which are the ones that have high inner product with the residuals from the previous fit. We look in each section and we look for whether there is one that is above threshold and add those columns to the fit. Stop at a step size of order log b. More precisely, it should be the signal-to-noise ratio times log b plus 2. Or stop if you can't find anything else above threshold. Quantities that arise in the study, or in the decoder, the algorithm, you initialize with the residual 1 equals y, and j1, the set of all columns. You loop through, updating your residuals, forming the test statistic, which is zkj equals the inner product between x and the residuals, normalized. The threshold is square root 2 log b. Sound familiar? It's what it should be, plus some a. We solve for the a that gives the least drop from capacity. Detections occur when z is bigger than tau. You add to the fit the sum of the right coefficients times the columns that were above threshold, and you update the search space for the next step. Now, other things could work, but we wanted to find something that we could study the distributional properties of successfully. And we actually, to do the distributional properties, we kind of do a reverse regression. Bayesians might, or inverse regression. Bayesians might like it. We look at the regression, we use y as a predictor of x and say x is some multiple of y plus something, some residual to it. And we study the distribution of those objects. And we indeed create, when we form this increment to the fit, we find the initial fit, you have y, and that starts in a kind of an adaptive Gram-Schmidt decomposition. The first column is y. And then after that, you use the parts of the addition to the fit that are orthogonal to all the parts that have come before, y and all the earlier fits. And we study the distribution of those quantities and their norms and produce iterative inductive proof of their distributional properties that enables us to study the behavior. And there's some simplifications that makes things easier. So when we track the progress, we have sent, which is J1 through JL. Those are the indices of the terms actually sent. False alarms occur when terms not sent produce test statistic values above threshold, and there's a total fraction of false alarms that occurs. Notice we take weighted sums. Those pi j's come from the power, the normalized power for associated to the section that J is in. That actually creates a need for large deviation inequalities like I put up earlier for the Bernoulli, but weighted Bernoullis. And the Chisar proof carries over very nicely to a nice information theoretic characterization of the error exponent for such weighted Bernoullis. If you don't do these weights, you can't get the inductive proof of the distribution properties. It took us a month to figure out how to set it up to, just to get started, for the second pass of the algorithm. So then you keep track of correct detections as well. And the key is to show that there will be a suitable growth in the expected fraction of correct detections. So there's this update function, GL of x. Its meaning is that if we have currently correctly decoded, say, 0.4 of the, in weight of the sections, then what do we expect will be the fraction we will decode at the next step? It's GL of x. This is a plot of what that function is for the specified set of parameters. And the key to the algorithm working is that the red curve G stays above the x line so that you are always making forward progress towards more corrected. You get stair steps that say where you're going to be next. The blue is slightly below the red because empirically the fraction that will be above threshold amongst the ones sent, you have to back off a little bit from expected value, and again in accordance with the large deviation exponents for weighted empirical sums of Bernoullis. And so with such, but as long as red stays above green, there's room for blue just below red. And as long as red stays above green, it can't stay above all the way up. And that plot, it looks like it goes all the way to 1. It doesn't quite. At the very end, it levels off. It asymptotes to 1. So that's why there's a remaining fraction of mistakes that that the method would need the Reed-Solomon code to take care of. That there won't be two competing code words that would be that close to each other. So that's the way it looks, and different signal-to-noise ratios get different steps, different pictures, and hence different numbers of steps and progress on those steps. And the analysis consists of verifying what are the rates at which this cumulative property will hold. And the key is that it has to get started. It has to start off okay, and already there you need the rates less than the capacity in order to get started. And then the question is, how much less than capacity so that not only does it get started, but makes it all the way, up to near a fraction of successfully decoded being up near 1. So to summarize the conclusions, we have error probabilities that come out of those large deviation bounds for the F hats and the Q hats. First, by a different scheme of analysis for the optimal least squares decoder, we can handle all rates up to capacity. It's just you don't want to get too close to capacity, or your error probability won't be that great, or your block length requirement will be so huge it's impractical, right? So you want to be off some. Now, with some schemes like polar codes, we don't even know how close to capacity. We just know fix an R less than C and certain asymptotics hold. Here we're trying to see how close to C we can get by a practical scheme. Unfortunately, our approach to capacity is slow. So there is this C sub B, which is within a 1 over log B from capacity. Nevertheless, at the rates that are comparable amount less than capacity, the error exponents that we achieve are suitably exponential. They're exponentials in L rather than in N, and that's because it has to do with large deviations of relative frequencies associated with the L sections. So the relevant asymptotics is in L rather than in N, although they're related to within a log factor. And if instead of, for the Qs, if instead of the Hoeffding inequality, if I use a Bernstein inequality, the variance calculation associated with the shaping of the power allocation gives a little bit of improvement in the exponent by a square root of log b. And that's nearly optimal. In terms of n, this ends up being like n times c minus r squared divided by log b to the 2.5. And if this difference is of order 1 over log b, and that's within a square root log b of the optimal exponent at those rates. So the rate envelope of how close to capacity you get is slow, but at those rates, the performance is favorable. It's the right type of exponential behavior. A lot of the work concerns, given that these log is such a slow function, we care about that C1, right? This is not one of those theorems where, oh, factor 2 here, a factor of 2 there, uh-oh, I'm at 1,024, oh, that's okay, it's just a constant. Log b ain't going to be bigger than that. So Anthony and I have struggled to produce the best C1 that we could. If you look at our website, my website, the last paper, and you can click on it and you'll see, a long paper that struggles to get the best constants we can. This is a somewhat cartoonish representation of it, because what we can say is when S and R gets small, we get something that's the closeness to capacity becomes more like 1 over square root log b. And then the closeness to capacity improves as S and R gets bigger. But then there's this thing, so that if S and R gets too big, it begins to hurt. You need B to stay bigger than a power of the square of S and R for the relative rate drop to be small, although we have ideas on how to get this down to a log C, so that you wouldn't need such a, but it's not a bad requirement to say that saying that your B would be large compared to S and R is not bad. When we run simulations on this, we routinely use B's that are like 128,000. So we can handle pretty large-sized codes. Okay? So I'm not going to go into the further discussion on those things. There's another decoding progress plot. Summary. Sparse superposition coding is fast and reliable at rates up to channel capacity. And the formulation analysis blends modern statistical regression and information theory. Thank you.